and we will continue our discussions on the flash. And today we will discuss the reliability issues. So the reliability issues in the flash memory generally include three aspects. The first one is called the endurance problem. So this is how many times you can program and erase the memory cell before the memory window is collapsed. So memory window is defined as the threshold voltage window between the program and the erased state. So basically, how many times you can write the data into the memory, how many cycles you can do this before the cell becomes dead. So this is the definition of endurance. And then the second one is retention. So this one is not writing. This is after you write, how long the memory cell can maintain the state. So this is called the data retention. And then the third aspect is this disturb due to the program or read. So this is when we select some cells to program or read, so the adjacent cell or the neighboring cells may be disturbed by this program or read operation of your selected cell. So those three aspects basically are these reliability issues in the flash. So if you compare this with other memories we discussed before, like the SRAM or DRAM, so many of those reliability issues are unique in this flash. And you will see that later. This is general for the non-volatile memory. Because for the SRAM and DRAM, they are volatile memory. And they don't have the endurance problem, because for the SRAM and DRAM, you can write many cycles, as long as, for example, 10 to the power 15 cycles or 10 to the power 16 cycles. So there's no problem with this endurance, because essentially you are charging and discharging. For example, your cap is not big problem there. But endurance is a very significant problem in the flash. Data retention, SRAM, as long as you have the power supply there, then your data is there. And DRAM, the DRAM's data retention, we discussed that 64 milliseconds, right? That is kind of the retention for the DRAM, and we have to refresh. So in general, you don't have a problem there because you do the refresh anyway. And this flash is non-volatile memory. That means you have to power off anyway. So then after you power off, how long can you maintain the state? How long can you maintain your data? So we will discuss this one by one. So first, let's look at the endurance. So this endurance degradation happens after the program and erase cycling. So you do the program, erase. This is one cycle. And you repeat this for many cycles. So this is general testing you are going to do if you want to evaluate the endurance. And this is the typical behavior of the endurance degradation. So here is the VTH state of this is the program state, this is the erased state. So initially you have this 4 volts, let's say more than 4 volts window between the program state and erase state. And then you keep doing this program and erase cycles. Typically you do it in this log scale. And then after that, you will see that the final trend is the erased state. The VTH will increase. That means what? That means you cannot erase the cell completely. You can only partially erase, because if you erase the cell completely, then it will go to this negative minus 3 volts. But right now you can only get maybe negative 1 volt. So you cannot fully erase.
Does this depend on, say, time? Like, I suppose in this test you charge or you either program or erase it, let it settle, and then do the opposite. Does it?
Doesn't matter. So you just you can do erase first and program later. Yeah, just you repeat this cycle.
But what I meant is, how fast do you do the program and erase?
So it may matter a little bit, but you know, Flash is slow anyway. So erase and program, you know, like hundreds microseconds. So it's slow anyway. So we need to understand what causes this increase of the VTH of the erase state. So basically, if you think about the tunneling mechanism we talked about earlier, the FN tunneling for this NAND flash. So the electrons basically tunnel through the tunnel oxide between the floating gate and the channel. So as the electrons travel through, so sometimes the electrons will be trapped in the tunnel oxide. So that means it cannot go through. So somehow it stopped in the middle, in the oxide. So if you have that, then here, for example, this is a floating gate. This side is floating gate. This is your channel substrate, and this is the tunnel oxide. This is a band diagram. And for example, if you get those electrons trapped into the tunnel oxide, then it will increase the barrier here because it's negative voltage applied to the band. The negative voltage will increase the barrier. So it will make more difficult for the electrons to tunnel out. That means you cannot erase all of them, because ideally you want all the electrons tunnel out from the floating gate, but now it's more difficult for electrons to tunnel out. Some of them are trapped in the floating gate. That means you still, some of them are trapped in the tunnel oxide. That means you still have partially electrons in this structure. So the VTH cannot go to very low value. So this is the problem for the cycling. So this memory window, eventually, if you keep doing that, then this window will collapse. And if you look at the typical number here for today's NAND flash as a function of the technology load, the endurance cycles are typically in this range, not very large. Okay, so this is a 10 to the power 3 cycle, 10 to the power 4 cycle, 10 to the power 5 cycle. So the best you can do is like 10 to the power 5 cycles. Okay, and this is for the SLC. We talked about this before, single level cell, 1 bit operation. So you can get the best endurance. But still with the shrinking of the feature size, then this endurance cycle tend to degrade. And if you are looking at the MLC, this MLC, then it actually is more worse. Here, you can only have like 10 to the power 4 cycles to start with, and with the shrinking of the feature size, you will go to like 1,000 cycles. So MLC is more difficult because you can imagine that here you want to have many states here, so any shift here will cause error in the result. So this is the endurance cycles with the scaling. So more and more difficult. And today's commercial flash you can buy from the market, the typical endurance like a few thousand cycles. Your SSD, each bit, you can only write it about a few thousand cycles. Of course, this is not end of the day, because even you have error, then in the system you will employ the ECC error correction code to correct the error. But of course, if you have lower endurance cycles, you are going to spend more on the ECC. That means your parity bits will get more. This is an overhead to the system, but you can recover that by the ECC. We are not going to discuss ECC in this class. If you take some memory system level classes, you may see the ECC there.
If I can ask, do they automatically employ those? They automatically put in ECC code or in the hard drive designs these days?
Yeah, ECC is by default there.
Okay, but I'm saying that it expands or changes, so it's not as though if one bit fails, the whole hard drive now.
No, you have ECC. Yeah. So, and also the other technique is called the wear leveling. Okay. So this is because if you look at the workloads, you write the data. The memory controller need to evenly distribute the write operations across different blocks. You don't want to write one single bit heavily, right? So when you do the write operation, then when the data, for example, you need to write some data, write your picture image, save your image to your SSD. So it will not save to a single location always. So there's a counter actually in the flash peripheral circuits. There is a counter to count each block, how many times you write the data to that block. And then the memory controller will look at the different block with different counter number, right? How many cycles you have done there. So then it will try to schedule the new write operations to the blocks where you have a lower value of the in that counter. So you will try to evenly distribute the write operations across the whole SSD. So there are some architectural techniques to deal with this. But from the device perspective, you can only write like a few thousand cycles on a single flash cell. And the retention, okay, so retention failure mechanism. So typically when we talk about retention, we need to consider the high temperature because first of all, you have to sustain like some higher temperature. For example, because you are in Arizona, for example, so you have to sustain higher temperature. So the higher the temperature, the faster the degradation of your data. This is because the electrons, okay, whether they are in the floating gate or trapped in this ternal oxide, no matter what, if you have temperature there, then the electrons tend to detrap, okay, because it has higher kinetic energy, so it will vibrate and then try to come out. So then, for example, after bake, okay, then the electrons may jump out from the floating gate. Then your threshold voltage will increase or decrease. If electrons jump out from the floating gate, your threshold voltage will decrease, right? So this is due to this temperature-induced detrapping process. And with the cycling we discussed before, some of the electrons will be trapped to this ternal oxide. So after bake, that means go through high temperature process, then those electrons will go out. And if you look at the mechanisms for the charge loss or electron loss, there are two mechanisms. One is the intrinsic charge loss due to this thermal process. So basically, as I just said, if you have higher temperature, the electrons tend to vibrate more, so they may jump out from the trapping site. So then if they jump out from the floating gate, if you look at this distribution of the threshold voltage, so this is MLC, 4 level, and due to the detrapping process, this is the detrapping process, then the threshold voltage tend to decrease, as we discussed. So the threshold voltage tend to decrease due to the detrapping. And there's another mechanism for the electrons to, let's say, move from the floating gate to the channel. That is through this defect of the oxide. So basically, the electrons, this is the floating gate, and then if you have temperature, so electrons will jump over this barrier of the thermal oxide. So this is due to the thermal process. The other mechanism for electrons to leak is through this defect in the oxide. So this is like the vacancy of the oxide. So if you lose one oxygen atom in the oxide, so it causes a vacancy of the oxygen in the oxide. So it will behave like a trap for the electron. So basically, electron can jump like a step stone. So electrons can turn the tunneling distance will become less. So electron will first tunnel from here to here, and then to here, and then leak out. So this is like a step stone for the electrons to tunnel through. This mechanism is called the trap-assisted tunneling, or sometimes it's called the SILC, stress-induced leakage current. So if you have the field stress across floating gate to the substrate, then the electron tend to leak through those traps. So no matter what, those electrons will come out from the floating gate. But for the SILC, the change to the distribution of the threshold voltage depends on the polarity of the, let's say, the voltage. For example, here for the program state, so the SILC tend to decrease the threshold voltage. This is because for the program state, you have electrons in the floating gate, so the electrons will leak through this tunneling path. So then the threshold voltage will decrease. But for this L0 state, which is the erased state, and in that case, then you have to think about the other way. So then that means here this is a channel, this is a floating gate, and then due to those stepstones, then electrons will go into the floating gate, and then the threshold voltage will increase due to this SILC, because in this case, the electrons will move this way. So this is a change to the distribution of the threshold voltage for different states. This happens over time. Okay, that's why this is called a data retention problem. So how do we characterize this kind of data retention problem? And the typical way to do this is to do this temperature acceleration test, because this process happens very slowly at room temperature. Okay. The data retention, or let's say the data loss, is very slow at room temperature. So you may see this kind of loss over years, right? Over maybe 1 year, 2 years. But as an engineer for this company, you cannot wait for like 1 or 2 years to categorize the error. So you want to do this in a faster time scale, and then the temperature will help you, because at higher temperature, then the electrons have higher kinetic energy, easier to jump out. So what you will do is to bake your chip at different temperature to accelerate this kind of degradation. And then, for example, let's look at this program state. It's start from here, the threshold voltage like close to 3 volts. So what you are going to do, of course, you can cycle the device many cycles, 10 to the power 6 cycles. This is post-cycling, and you are looking at the end of the lifetime of the cell, and then you do the baking, okay, at different temperature from, let's say, 150 degrees C up to 300 degrees C, and then you will measure the threshold voltage over baking time. This is in the minutes, okay. So you are not waiting for years. So you are waiting for like maybe a few hours, a few days, okay. Then, due to this loss of the electrons, then the threshold voltage will decrease over time. But as you see here, 150 degrees C, these black ones, so the degradation is the slowest. And then as you increase the temperature to 300 C, then the degradation will become faster. So you will get this kind of data. And then what you want to do is to project what is the data retention time at, let's say, lower temperature of interest. Because we are not going to use your chip at 150 degrees C anyway. You want to understand what is the retention time at lower temperature. For example, 85 degrees C, if you assume that is the maximum operation temperature you are going to have, then you look at the retention time at 85 degrees C. So what you need to do is to do this extrapolation, okay, or projection. So from this raw data, what you need to do here is to, for example, define a criterion for the failure. Okay, so for example, if you think that if the threshold voltage drops to 2 volts, you define it as a failure. So you draw a straight line here, and then you will get different retention time for different temperature. Then you will have one-to-one mapping, right? So this is 150 C, and this one is 300 C. So you have 4 retention time corresponding to 4 temperature, okay? Then you need to draw this plot, okay, called the Arrhenius plot, or sometimes we call it 1 over KT plot. This is because the retention process is governed by the thermal process. If you have any thermal process, then you can always express the retention time as something like this. This is some coefficient, and this is your retention time, and then this is the temperature in terms of KT, and then EA is called the activation energy. Okay, so this is the equation you need to use. So what you want to do is to extrapolate, okay, this plot. So what you get from the testing data is this retention time versus the temperature T here, okay. And then in this equation you have 2 unknown. One is T0, one is EA, okay. So then you need to derive those EA and T0. So what you can do here is to translate this formula into this plot. You need to take, for example, for the retention time here, you want to take a log. You take a log, Okay. So here you draw it in the log scale in the y-axis. Pay attention to that when you convert the natural log 10, let's say natural log to log 10, there is a coefficient 2.3 there. Because natural log 10 is 2.3. Just be careful there. And by the way, you have homework on this. Okay, I will not tell you every step, but I will try to go over the process here. So then, first you convert the retention time log scale here, and then for the x-axis, you want to take this 1 over kt, or 1 over t sometimes. You can use 1 over kt. It's the same thing. K is this Boltzmann constant. And you use 1 over kt as the x-axis. You need to convert the temperature first from the Celsius to the Kelvin. Okay, this T is in Kelvin. Okay, in Kelvin, the scientific temperature. Okay, and then you have kt, and then you take 1 over kt. So after you do that, then those points should be in a straight line in this point, in this plot. For example, here you have maybe 3 points or 4 points. Maybe let's use this example. We have four points from the left figure, right? 4 temperature correspond to 4 retention time. So that means in this plot you should have 4 points, okay, correspond to those 4 points here. You just need to translate the figure, the raw data, from the left figure to this Arrhenius plot. Okay. The reason you want to do this is because you want to draw a straight line to extrapolate the slope, because this slope is what? Any idea? Which parameter? EA or T0? Any idea? EA. Okay. You can do this math by yourself. You have 2 variables and then you play around. You will get that. Basically, you translate that exponential function to like y equals to AXB format eventually, right? So your y-axis is in the log scale of t. If you take log of this equation, then you will convert this, and then if you think y is like log t, x is 1 over kt as a variable, right? Then you change your plot to the linear scale. That's why you have a straight line here. Is this clear? So essentially the slope will give you the EA, and then if you extrapolate this, I think to somewhere you will get a T0. Okay. The intersection. But what matters is EA. Okay. Because once you get the slope, then you can extrapolate. So you get you can extrapolate, and then you can mark 10 years here in this plot, and then you look at this. Okay, for example, for this line, this is at here, and you read out this KT value and back calculate what is the temperature. So basically, it says that if the intersection extrapolation is to this point, basically says that this cell can sustain the temperature 114 degrees C for 10 years. Okay, so this is very good.